So I'm really pleased today to be able to welcome Carolanne to come and talk to us today. So Carolanne's a fairly new lecturer at Sheffield University, but she's done her PhD on ventilation, particularly looking at ventilation in schools and some work on CO2 monitoring. So really pleased that Carolanne's going to come and talk to us today. So I'm going to hand over to you, Carolanne, to share your presentation.
Thank you. So we tested this, so it should work again, but I'll try and check. Can you see this okay?
Yep, perfect. Thank you.
Great. And hopefully you can hear me, so it's all good. Technology did not fail us. Yeah, so thank you everyone for joining today, and thank you to CAF for the introduction. I'm Carolanne Vouriot. I'm a lecturer in building physics at the University of Sheffield. And today I wanted to talk about the work I've been doing using CFD to kind of investigate the validity of CO2 point measurements in naturally ventilated classrooms. So this is work that I started in my PhD, and I've kind of been continuing and publishing about this. So it's hopefully it should give you a good overview of what I've been up to. So I briefly wanted to introduce the setting. So as Kath said, I focus on classrooms specifically, and that's because the indoor air quality of classrooms matters to a lot of people. So in the UK, this is 11 million pupils and staff that regularly attend schools, so that's almost 15% of the population, and they spend a large proportion of their time in schools, but specifically in classrooms indoors. So the air quality of inside classroom can have a direct impact on their health and their well-being. And specifically in schools, it can also impact how well they do academically, and their learning performance. So clearly, it's a setting that matters to a lot of people. But unfortunately, it's also a setting where previous studies, and that's in the UK, but also in Europe and in the world more widely, it's been shown that there's a bit of an issue. So previous measurement campaigns have shown that the ventilation provision sometimes in classrooms is insufficient, and they found quite high level of pollutants. So clearly there's a problem here, and we want to, the kind of motivation behind my work is to try and improve this to make sure that we kind of provide suitable environments for learning where pupils and staff can spend a nice amount of their time. So one solution that's it's been kind of coming up and developing in the past few years is CO2 monitoring. So this is something that we've been able to do for a while, but now it's really becoming more widespread and relatively cheap. So you have example of those sensors here at the bottom, which are quite low cost, which means that you can monitor classrooms for maybe a longer period of time than before, and kind of a large scale. And this was really kind of maybe one benefit of the pandemic was that it really became a lot more widespread. So this article here kind of came up when the DFE decided to deploy CO2 monitors widely in every classroom in England. And that's because they can be very useful to practically manage ventilation provision. So in classrooms specifically, the main source of CO2, except if you have a roaring fire in the classroom, the main source of CO2 is people. So if you know about the occupancy, you can then use this as a proxy to get a better idea of what the ventilation provision might be. And this, in the pandemic especially, can be useful to get an idea of what the risk of airborne infection is. So that they can be very useful tools. And I think there's clearly a big potential with those sensors coming in, but they also, as with any tool, they have a few limitations. One that can't be underestimated, of course, is that it's great that you can measure loads of things, but you need to make sure that this data is of good quality. And so a lot needs to be done to better understand the accuracy of the sensors, how they behave in time, whether they drift or they need to be recalibrated. So that's not my expertise, but I'm just saying that this also needs to be taken into account. The other thing is we need to understand, in order to interpret the data coming in, we need to know what's happening in terms of the occupancy as well. So clearly we need to know how many people there are to then be able to make some predictions about the ventilation provision, for example. And the last aspect, and the one that I'm kind of interested to look more into, is that you can't fully measure the 3D CO2 concentration filled in the room. So you're limited to a number of measurements, and quite often for practical reasons, that might just be one measurement in the classroom. And so what I was interested to look into with my research is whether this can be representative of what's happening in the whole space. And when it comes to ventilation, where it's a bit challenging is that most of the classrooms in the UK are naturally ventilated. So that means that their ventilation is mostly done maybe through windows, and it relies on natural forces like buoyancy and winds, so it can't really be controlled. And we also expect that there'll be some kind of non-uniformity in terms of the ventilation provision and maybe in the CO2 concentration field in the room. It's not well mixed and it might not be uniform. And so that's an example, for example, on the right, this is a teaching room in Cambridge. Actually, this is mechanically ventilated, but it really highlights the kind of non-well mixed spaces you can have. With here, the smoke cues, there's a tracer, and you can see how it just lies there, just right in the breathing zone. So you could see why that would be a bit of a challenge. And of course, if you only have access to a point measurement of CO2, then that does raise the question of whether that's even representative of what's happening in this space. So the way I've been looking at this problem is using CFD, and I kind of wanted it to kind of place it in terms of what's been done before and how you actually study this problem of looking at ventilation. And the way I think about it is that it's a bit of a spectrum. You can go all the way to realistic existing classrooms. So very specifically going into a school and looking at a specific classroom and measuring it with as many sensors as you want. And that's really good because it actually tells you about the real conditions and you know what people are experiencing. The problem with this, the challenge, I guess, with ventilation is that loads of different factors can impact what you measure and to try and interpret what's the different effects that's happening. So that's quite, it's a difficult problem to kind of tackle from that angle. So the way this problem has been looked at is kind of making it, kind of simplifying it and going more towards the more fundamental fluid dynamics problem of trying to understand how ventilation is driven and how that affect the flow in the classroom. And so typically, natural ventilation and buoyancy-driven ventilation has been studied a lot with small-scale experiments when instead of air and heat, you use salt and water baths. And that's been really useful because then you can kind of boil down the ventilation system to the key components, in this case, the heat source, whether it's localized, distributed, and the vents, so where they are. And so that's been really good for this case, for example, for the displacement ventilation. It's kind of allowed to kind of simplify the problem and see that the flow rate that you're going to get depends mostly on this the effective area of the vents. And so this type of boiling down the problem allows you to do kind of quick predictions about the ventilation provision and also the kind of flow patterns in the room. So I've kind of come into this problem from that side of trying to boil down the problem of looking at ventilation in classrooms to kind of simplified components and looking at that with CFD. So with the main problem that I want to look at being how do you look at how does the ventilation pattern created by buoyancy driven forces affect the CO2 distribution in a room and whether that impacts the accuracy of the point measurements they might make. So this is the kind of simplified case that I've been looking at. It looks very different to maybe what you think of a classroom, but it does capture the key components that are involved when it comes to providing ventilation. So it's been sized on a primary school classroom, so the kind of typical size that you might see in the guidelines with 32 occupants and looking at winter time. And here, as I've mentioned, it's quite simplified. So the occupants are not explicitly modeled. Instead, they're accounted for mostly through the heat they're generated. And because we're assuming it's a classroom and students are kind of sitting uniformly, this is inputted as a distributed heat source on the floor. And then they're also modeled through the CO2 they might generate. And once again, this is this kind of gray area you see at breathing heights. That's also assumed to be uniformly distributed. And because I was quite interested to look at what the effects of ventilation. This has been simplified as well to consider kind of displacement ventilation. So the openings are on the floor and the ceiling, which is a bit different to what you might see. But the idea with this is that it kind of captures the ventilation flow that's provided. It's being driven by this heat source, but then you kind of get rid of problems like bidirectional flow by having horizontal openings here. So it is a bit of a simplification, but it really allows you to look at the effect of the ventilation pattern on the CO2 distribution. And because the CFD, you can play around with loads of parameters. So one of the parameters that I looked at was looking at the effect of having that top vent either on the opposite end of the classroom, so that's the opposite-ended configuration, or on the same side as the bottom vent. So I did those simulations using OpenFOAM, run simulations, and the buoyant pumple foam solver. And what was quite challenging with this setup is that I didn't want it to impose any specific ventilation flow rate at the boundary conditions at the vents. So instead, it's purely buoyancy driven. So that distributed heat source at the floor is what's driving the flow, which is what you have in real life. And so that's a bit of a challenge to set up numerically. And so I had to include those kind of exterior domains to have a nicer inflow and outflow. And as I mentioned, CO2 is inputted as a passive scalar at breathing height. And because of CFD, you can add loads of other scalars. So I also introduced 9 different scalars to account, to look at what would happen if, say, there was an infector in a room, how that might impact predictions you might make when it comes to exposure. And once again, this is highly simplified. So each occupant has not been explicitly modeled. That would be a lot more challenging to do, which means that you can't really make any conclusions about what happens in a near field of occupants. Instead, you kind of have to come to kind of broader overall room distribution. You can't really look at what happens in the near field of an occupant. So the kind of infected breath scalar, for example, was not inputted. Was it inputted as a volumetric source, so over the area where the person might be. So you can't really look at the near field, but instead you have to look at the far field. And so the first thing that came out of this was maybe unexpectedly, you had very different ventilating flow patterns between those two configurations. So on the top, this is the opposite-ended configuration, and the bottom is the single-ended. Here the streamlines are plotted, and so that kind of follows the flow as it comes in through that bottom vent and up to the top vent, and it's colored by the edge of air. So basically, if you're in the kind of yellowish colors, the air is quite new, it's quite fresh. And then the darker, more purple it gets, the longer it's been in the room, and the kind of, the way to think about it is the kind of staler it's been. And what's quite interesting, and maybe counterintuitively, is that the average CO2 concentration in the case where the openings are on the same side of the classroom is lower than the other case. And that's despite the fact that the ventilation flow rate is the same. So clearly the flow pattern has a big impact on the CO2 distribution. And that can be captured with the removal efficiency here. So that is as a metric that just allows you to kind of quantify how effective your ventilation is at flushing out that CO2. So if the room was perfectly well mixed, it'd be equal to 1. And so in the single-ended case, we can see that it's better than 1. So it's kind of indicative of a kind of displacement ventilation efficiency. And so because it's lower in that opposite-ended case, that's because you have this big area here on the top left, where you kind of have stagnation zone where the flow is not really going there. And so concentration of the scalar basically can accumulate, and that raises your concentration. And that's quite different to what we expected when we started doing those simulations. So that top left picture here is kind of what we thought would happen with a distributed heat source. We thought it would lead to a kind of uniform temperature distribution, and also maybe quite uniform CO2 distribution. And that wasn't the case, as I've shown in this streamline. And what's quite interesting is that This was also shown kind of roughly at the same time by Tom Higton, who was doing his PhD at the same time as me, with those saltwater bath experiments that I was talking about. So his setup was slightly different because he had a door as the low-level vents instead of the kind of vent on the floor that I had. But otherwise, he also used a distributed heat source, and he also had that high-level vent. And what you can see here in this video, the flow has been allowed to kind of settle, reach a steady state. And he bursts a balloon with dye, which is neutrally buoyant, just to visualize what's happening in his room. What's quite interesting is that he sees the same kind of flow as I saw in my simulations as well. So the kind of cold incoming air, well, here water, but representing air, kind of getting progressively warmed up, but not rising up to the opening until it reaches the far end wall and then can exit through the top opening. So that clearly, because of this kind of recirculation pattern around the domain, that's why your top vent has such a big impact on your ventilation efficiency and the overall CO2 concentration or scalar concentration you get in the end. And so those types of flows we hadn't really seen in this kind of ventilation scenario before, but it's something that's been looked at maybe in more detail in the context of oceans. So that was quite interesting to see. Because I could with CFD, I then played around with kind of changing the openings, the size of the openings, to see how that would affect the flow field. So this is in this opposite-ended case, which had this big stagnant zone. So as I mentioned, what matters in those types of setups is the effective area. So if you have a larger effective area, you can typically expect a larger flow rate. And then I also played around with the ratio of the two openings. So in this first simulation that I showed, the top vent was half the size of the bottom vent. And so what I wanted to see whether this could also influence the flow pattern you got in the room. So the first thing I did is I set up simulations with smaller opening areas, so ones where you would expect a lower flow rate. And in the one on the left, I kept the same ratio of the vents, so the top vent was half the size of the bottom one. And in the one on the right, I made that top vent even smaller compared to the lower one. And so you can see how the two kind of flow fields compare. You do still get this similar pattern that I showed before with a big stagnation zone in the left, but then you do have very different removal efficiencies. So by changing the vent area in that simulation on the right, I've made the ventilation efficiency even worse. So it's lower than 1 now, which shows that it has a big stagnating region. So this shows that in this context, not only the effective area is not the only thing that matters, the ratio of those two vents is also quite important. And then going to the other side, I increased the effective area, so kind of doubling the flow rate if you want. And same thing, in one case, I kept the same vent area ratio, and in the other one, I made the top vent even bigger compared to the lower one. And that also, that one on the other hand led to quite different flow fields. So I think the one on the bottom left is still quite similar, but the one on the bottom right is very different, where you have this kind of flow coming in rises so much, this fountain, that you're kind of, and you end up destroying the stagnation zone, which means that you have a removal efficiency that's much higher. It's almost as close to the one you had for the single-ended case. So that was quite interesting. So we can see that clearly where your openings are in this specific setup impacts the flow pattern in the room, and it impacts the ventilation efficiency. I guess what's interesting now to consider is how it affects the distribution of the CO2 within the room. And so this is the results you get for this kind of original setup. So the one that I showed at the start, not looking at changing the flow rate that much. On the left is the PDF of the CO2 in the entire classroom. So for both the opposite-ended and the single-ended cases. And on the right, it's in the breathing zone specifically. So where kind of between the heights where you expect pupils to breathe in. whether they're seated or standing. And so you can see that clearly there's big variations, and this is even more pronounced in the breathing zone. And in both of these kind of zones, the opposite-ended setup is worse. You have higher CO2 concentrations. And if we want to kind of delve a bit more into the breathing zone, this is the kind of distribution you get in CO2 in this breathing zone, with kind of big areas, stagnated, areas of stagnation in the opposite-ended case, where you have higher values of CO2. So that's, yeah, so clearly you have, yeah, the space is not well mixed, and you have big variations in CO2 concentration. What I was interested to see as well is, practically, when you measure CO2 in a classroom, you want to put it out of the way. You might not be able to measure in the middle of this kind of cross section here. You have to quite often put it on a wall so that it's out of the way and it's practical. And I was interested to see whether this was appropriate, and whether using wall measurements you could capture what was happening in the room. So the way I looked at it was looking at those PDF of the CO2 concentration again, at specific heights, and comparing the kind of PDF of the CO2 concentration you have if you consider the whole cross-section at that height, or if you only consider the measurements that are taken within 20 centimeters of a wall, which is what I define as at the wall. And here you can see how they compare for both the opposite-ended and the single-ended configurations. And once again, opposite-ended is much more spread out. But what's quite interesting is, in both cases, the median for the kind of your wall measurements is very close to what you get over the entire cross-section. In a way, that's quite reassuring. And then you can also look at what happens if you look at different heights. So that's lower down in the classroom, and then higher up. So lower down might not be that interesting in this context to look at if you want to measure, because you're measuring below the kind of breathing height, so below where CO2 is generated. But above, you do get kind of measurements that are a bit closer together. The spread is smaller, and then once again, the measurements that you measure at the wall is kind of close. If you look at the median or the standard deviation is close to what you get in the whole cross section. So in a way, that's quite reassuring as well, that it shows that wall measurements for this kind of idealized setup are not too far off to what you get in the rest of the classroom. So clearly CO2 in this kind of idealized scenario, CO2 is not well mixed and is not uniform in the classroom. But what matters when we use CO2 is, quite often we use it to then infer something about the ventilation provision. And the simplest way to do this, and this is to use a kind of steady state assumption to find the flow rates. So there's a few challenges with this. You have to assume that in the time that occupants have been in the room, the CO2 concentration has kind of reached a steady level, and that allows you to infer back the ventilation rate. So it is an assumption, but it's quite an easy one to make, and it's quite practical. And using this assumption, you can find the flow rate from using the CO2 measurements, so the one I've been talking about. So something where you have a sensor and you'll just measure your CO2. You'll also need to know about the outdoor CO2 concentration, and that's useful because it will tell you kind of what's the concentration, the CO2 concentration of the fluid that's coming in with the ventilation. And then it also depends on the source term, Ng here, which depends on the number of occupants and the CO2 they generate. So I thought it'd be useful to compare how the kind of uncertainty introduced by those variations in CO2 compares to the other uncertainties you might have with those other terms. So in the simulations that I've shown, they should tell you about what types of uncertainty you might get in terms of the CO2 concentration you measure. And for that point, there's kind of two effects. One is that you might have a very different, because the space is not well mixed, your removal efficiency might be very different to what you expect. So if you were to measure the CO2 concentration in the single-ended case, where it's a lot more efficient, and assume this to be kind of a well-mixed average concentration, you're actually going to overestimate the ventilation efficiency by up to 20%, 25%. That's because your ventilation is a lot more affecting or flushing out the CO2. So that's one of the effects. The other one is the one I've been talking about. So this kind of CO2 concentration variation in the room. And just looking at, for example, the interquartile range that I showed for the kind of original setup, this can lead to variations in the ventilation flow rate you predict by up to 30%. So that's kind of showing the effect of using a point measurement of CO2 on the kind of ventilation flow rate you predict. But then, as I said, this has to be put in the context of what else you need to know about the room to make those predictions. And if you assume that the CO2, the outdoor CO2 concentration, typically, I think unfortunately, it's not always measured. So you kind of just assume it to be equal to 400 ppm or something like that. But even if it is measured, I think it is quite sensible to say that a sensor like that might have a 50 ppm accuracy. And this variation in 50 ppm can lead to maybe up to 30% difference in your prediction of ventilation flow rates. So clearly that also needs to be taken into account when you predict your ventilation flow rates. And the last, maybe more challenging kind of parameter in this equation is this source term. And that's challenging because the CO2 generation rate will vary very differently from individual to individual. And even if you were to take population average, you also need to take into account the sex, the age, and the activity of the occupants. So I've summarized here the kind of CO2 generation rates that you get typically for primary school age children doing a range of activity that seems sensible in the classroom. So 1.2 METs kind of sitting quietly, 1.6, they're starting to move about. And so just accounting for this type of variation, maybe plus or minus 5 occupants going from this kind of level of activities for primary school age children, that can lead to variations of up to 70% in your predicted ventilation flow rates. So when it comes to the uncertainties introduced by using point measurements of CO2, they're not negligible. And clearly, if you have a naturally ventilated space, assuming that it is well mixed is a bit of it's quite a big assumption. But it needs to be seen in the context of those overall assumptions that you have to make when you infer the ventilation prediction, the ventilation provision. And clearly, knowing more about the occupants and what they're doing would help kind of improve the accuracy of your predictions. The other aspect that I wanted to talk about is when it comes to using CO2 kind of make indoor air quality assessments, is using CO2 to do some infection risk modeling. So I'm going to plug in some work that I did quite early on with CAF as well. And that's quite useful because CO2 allows you to get a measure of what the rebreathe fraction in the space might be. So that's the amount of air in a space that has already been breathed out by another occupant. And in the context of infection risk modeling and airborne infection, this is very useful because if you assume there's an infector in the room, this fraction allows you to kind of quantify the chance that someone else will breathe in their viral particles and get infected. So this is this type of modeling was done. I did this looking at classrooms with COVID-19. So kind of assuming that one infector regularly attended the classroom, you could calculate the number of secondary infections arising just for looking at airborne transmission in this one setting. And it's quite useful, for example, because you can see monthly variations. So here, just from CO2 measurements, you can show that the chance of getting infected in January is much higher than in July. And that's because the ventilation supply might not be as big. So that's clearly it's quite useful. But then once again, we know that CO2 varies quite a lot in the space. So does the accuracy of your prediction of your measurement of the rebreathe fraction, how does that vary depending on the infected location? So as I mentioned before, in those CFD simulations, I also introduced 9 different scalars. So that's a cross-section of the room. And these were to kind of try and see the effect of 9 different infectors in different locations in the room. So the way you can assess whether CO2 is is a useful proxy for infected breath is to compare the distribution of this specific passive tracer to the overall CO2 distribution. And so the way I looked at it was to look at this ratio, which is the ratio of the exposure to infected breath compared to the kind of exposure you can estimate from local CO2 measurements. And so what you can see here, the way to interpret this basically is if this ratio is quite high, so in those kind of orange regions, you're likely to underestimate exposure by using a local CO2 measurement. And that makes sense, right? It's very high in this case, close to where the infector is. And that's because you can't pick up this just by using a local CO2 measurement that accounts for all the other occupants in the room. So clearly, the accuracy of using CO2 as a proxy will depend on the specific infector location, but also on the overall ventilation pattern in the room. So in this case, we're looking at the single-ended case that I was looking at. But then if you change to the opposite-ended case with the top vent at the other end of the room, that changes how the accuracy of this ratio, as you can see here. And in some cases, like when the infector is at the bottom left, so here on the bottom left figure, the area where you're likely to underestimate the risk starts being quite a large proportion of the room. And that's because in this specific ventilation configuration, you have a big stagnation zone. So if your infector happens to be sitting there, their infected breath will not be flushed away as efficiently as in other positions, and so the risk increases and that might not get picked up by the CO2 proxy. So these plots are summarized in this kind of box plot for all the infector locations and for each ventilation configuration. So here, this box plot kind of shows you how accurate your local CO2 measurement is. So either in those 9 different locations, but also at the walls. And here, at the kind of warm local measurement is kind of within the range that you see elsewhere in the room. So once again, those wall measurements don't seem to be more of a particular issue. What was quite interesting is because I had those simulations with quite different flow patterns by varying the flow rates, I had a look at how this affected the accuracy of this ratio and whether that changed things a lot. So here I've kind of picked out the 2 extreme cases. One where the removal efficiency is a lot worse and your stagnation zone has even grown. And the other where the case where you kind of destroyed the stagnation zone because the fountain was rising so high. And so you see the same kind of plot, this ratio of infected breath exposure to CO2 exposure. And so clearly you are more accurate in the case where you have a higher removal efficiency on the right. But even in this case where you had the big stagnation zone, when using the local CO2 as a proxy, you're still within a factor 2 of the exposure to infected breath. And here I just want to stress that this is not the risk of infection that we're looking at. It's really, we're looking at how accurate the exposure we predict from a local CO2 measurement is compared to the actual exposure to a specific infected breath. So even in those 2 cases with quite big flow rates, you do see this variation in how accurate your prediction based on the local CO2 is, and that depends on the ventilation configuration, both the kind of relative position of the openings, but also their sizes and the flow rates, and also depends on the infector location. But the point I want to stress here is that even if this does vary, and clearly there are local variations, you're still, by using the local measurement of CO2, you're still within a factor 2 of the actual exposure to infected breath that's been modeled here with the specific scalar. And if you put it back into the context of airborne infection risk modeling, you have another factor here, which is the contact generation rates that quite often you have to kind of estimate from past outbreaks. It will depend on the specific disease. And this factor alone can vary by up to 4 orders of magnitude. So clearly, there is some inaccuracies introduced by using a point measurement of CO2, But in the context of risk infection modeling, one where you might not know where the infector or who the infector was, and you might have to estimate a quantity generation rate. This inaccuracy from CO2 point measurements is just one of the factors that you need to account for. So hopefully in this talk, I've shown that CFD can be a useful tool to better understand how ventilation affects the fluid field in the room, and how you can use that to get a better idea of the uncertainties that you get from using point measurements of CO2. And I'm hoping that I've highlighted that when it comes to both ventilation provision prediction and infection risk modeling, CO2, the kind of CO2 distribution is one of the sources of uncertainty, but there's a lot more that we need to know to get accurate predictions, whether that's knowing more about the occupants, their activities, or getting a better understanding of this kind of contact generation rate. So the simulations I've shown, if we go back to this kind of spectrum from fundamental fluid, very idealized setup, all the way to existing classrooms, clearly they're just maybe one step towards more realistic case, but they're still quite idealized. So yeah, I think that the idea that I would like to look at is how you can start making them more and more realistic, so you can get closer to what you get in real life. So that's all for me. Thank you so much for listening, and I'm happy to take any questions if